Hi everybody, in this video we're going to do one more day of L'Hopital's rule. Now you'll notice down at the bottom here, we've already finished then with having to do the natural log in order to solve. We're going to go back to these algebraic manipulations, and in fact this video is going to be pretty short. I'm just going to be demonstrating to you some questions where it appears as though L'Hopital's is necessary, but it turns out we are supposed to solve it in a different way, hence these algebraic manipulations. So this first one comes from the Thomas book, and I've kind of simplified what it was trying to explain to you. L'Hopital's can't solve the limit, as you will continuously need to keep doing L'Hopital's, and we have to solve this in another way. First, I just wanted to demonstrate to you how L'Hopital's is going to continuously happen. This first one is going to be indeterminate. We know that we got 1 over cosine of pi over 2. For the other one, sine of pi over 2 over cosine of pi over 2. And this one becomes 1 over 0 over the bottom there is going to become also 1 over 0. We would treat this, since it is from the left-hand side, let's see, those would both be infinity. We would get infinity over infinity. So we know that that is going to be indeterminate. So if we were to do our derivative then for the top and bottom, derivative of secant is secant tangent. Derivative of tangent is going to be secant squared. We could cancel out a secant from top and bottom. And now that leaves us with tangent over secant. Then if we were to evaluate this, well, we already checked from before. We knew that this ended up being infinity over infinity. Well, as pi over 2 goes into tangent, that again is going to become infinity. We put that in for secant, we're also going to get infinity. So we would have to try doing L'Hopital's again. And perhaps you have a prediction already of what's going to happen. We're going to get secant squared on top. We're going to get secant tangent on the bottom. We would cancel. And now we're back to what we started with. So that's showing you how L'Hopital's is not going to solve this question for us. We're never going to be able to stop. So instead, we need to find a different way. Fortunately for this example, it's actually going to be quite easy for us. We just need to know what these trig functions are, and then we could simplify. And perhaps you saw that earlier when I was trying to show you what this was going to be equal to. We can rewrite this as 1 over cosine on top, and then on the bottom, sine over cosine. Now, we could cancel out the cosine from both this fraction and from this one that's in the denominator for each of those. And then all that's going to be left is 1 over sine. And then we can put pi over 2 into that sine of x. And from the unit circle, sine of pi over 2 is 1. And it turns out this was just going to be 1. So that was quite easy. Even though it's originally said that L'Hopital's was not going to be possible, it made it seem like it was going to be difficult, but this question really wasn't that bad. So I've got another one then from the Thomas book. This one I want you to try on your own. I'm going to give you a hint. In order to solve this, you are going to need to use a negative exponent. Give it a shot. This one I do think is going to be kind of tough though, so don't feel bad if you get stuck on it. Pause the video. When you are done, I'll show you how to do it. Okay, so as I said, this one here, my recommendation is that you're going to need to use a negative exponent, and I'm thinking let's take that e to the x and let's move it up to the top. So if we were to do that, we would have limit as x approaches infinity of, and then we would have e to the x squared times e to the negative x all over x. Then what I'm going to do is I'm going to combine these e's up here at the top. And so the exponents, we know then that when we have the same base, they are supposed to they're supposed to add, but because it's x squared and a negative x, they're going to end up subtracting. X squared minus x, and then the denominator is still x. Now, I'm thinking, even though the directions say we're not supposed to do L'Hopital's repeatedly, I'm still going to try to do L'Hopital's. And here's why. If we put in infinity at this point, we're going to get infinity minus infinity for the exponent, so that clearly is a problem. We would have infinity in the denominator. It's not looking too good for us. But at least from what we have here, this is telling me, especially this part right here, it's telling me that L'Hopital's is allowed to be done. So I'm going to go ahead and do that. Up at the top, we are going to get, I'm getting ahead of myself, sorry. We recopy what we started with for e, and then chain rule tells us that we have to multiply by the derivative of the exponent, and then down in the denominator, we're just going to be left with 1. Now that we have this, I'm thinking we need to simplify this somehow. So my thought is perhaps we can break this up into 2 limits. We could do limit as x goes to infinity of 2x minus 1 times, and then the limit as x goes to infinity of e to the x squared minus x. So what we can do next, this first limit, we can find the value of that. If we put infinity in, that first limit is just going to be infinity. So that's fine. Now for the second limit here, I'm going to take what we have and I'm going to turn it back into what it was originally, e to the x squared over e to the x. And here's the reason why I'm going to do that. If we were to put infinity in here, yes, I am well aware that what's going to happen is we're going to get e to the infinity over e to the infinity, and we're going to get infinity over infinity. Yes, that's still indeterminate. No, we are not allowed to do L'Hopital's here. But I'm going to explain something to you, and I hope this makes sense. I'm not fully sure if it will, though. This is actually going to be something that we were going to do later in a couple weeks, maybe next week, I don't remember. But regardless, we were going to talk about relative rates of growth, and that's what this limit is involving. The idea of relative rates of growth is actually quite simple, and it's something back to what we did in term 1. We just never called it that. You remember when we did these limits, and I talked about, let's just say, x squared plus x plus 1, and then down the denominator we had x minus 5. And what we did was we said we were going to look at the highest degree in both the numerator and denominator, and if the top happens to have a larger exponent than the bottom, then we knew that this was going to be positive or negative infinity. If, let's say then, we don't have that, and this was actually x squared down here, and we just have x plus 1 on top. This time, because the denominator had a larger degree than the numerator, this was going to be 0. And then the last one was going to be if they happen to have the same power, then we just did the ratio of the leading coefficients, and the answer was 2. So the review of that is related to this because if we look up at the top, our exponent, we clearly have a larger exponent in the numerator than we do in the denominator. What that means then is that the top is going to be growing faster than the denominator. And if we put infinity into both of them, this is going to be a little strange, but I'll try to explain it the best I can. This top then is going to get to infinity faster than this one will as we put larger and larger values in for x. Therefore, if the top is going to grow faster, then we could say that this second limit is also infinity because the top will be growing faster than the bottom. A way to explain this, let me try. Here, we're going to start with something like this. Let's pretend that we have 10 over 1. Now we're going to square. No, that's bad. Let me do a better one. Let's do 10 over 3. We know 10 over 3, that's 3.3 repeating. Now let's say that we're going to square both of them. We get 100 over 9. This is going to be a lot larger. It's going to be getting bigger than 3 and 1/3. Let's square both of those numbers again. Now we're going to have 10,000 on top. We're going to have 81 on bottom. That's even larger than the number we had before. The top is clearly growing faster than the bottom. So this is going to go, if we kept on going forever, that pattern is going to eventually lead us to infinity. So that's why that second limit has to be infinity. Okay, now that we have established that, to finish this off, we get infinity times infinity, and that is going to be infinity. By the way, this question is in the homework. My answer key currently doesn't do this question well. I'm thinking, though, of redoing the answer key so it's a little bit more clear. There's one more thing that I wanted to show you as well. This wasn't in my original notes, but I thought that this would be useful too. So we are supposed to use a limit in order to find the horizontal asymptote for this equation. Now, what we're supposed to do, as it suggests, start with a limit. And what we need to know is that for horizontal asymptotes, so I'm just going to draw a rational function like this. Our horizontal asymptotes are found by setting our limit to approach infinity. So that's what we're going to do for our first step. Then we know that in order to solve this, by putting in infinity just at the beginning, we get infinity times tangent of 1 over infinity. And this is going to become infinity times 0 because this part would have been tangent of 0. So that's not going to work. We need to find a way to simplify this. So let's go ahead then and take this x and move it to be underneath tangent. That means that we're going to get the limit as x approaches infinity of tangent of 1 over x over 1 over x. Now, even if we put infinity in here, we're still going to have a problem. We're going to get tangent of 0 again. We're going to get, this time, 1 over infinity, which is also 0. We're going to get 0 over 0. It's indeterminate. That is going to suggest to us then that we need to do L'Hopital's rule. Now, before we actually do that though, I have a different recommendation, and that's why I wanted to include this as an example. Rather than using L'Hopital's, let's do a substitution. I'm going to let u be equal to 1 over x. Now, we're not going to find a du. There's no derivative in here unless we were to do L'Hopital's, but even then there's no dx, du, anything like that. I'm just going to let u be equal to 1 over x. That means then that our limit will now become tangent of u over u. Now, there's one other thing that we need to figure out, though, which is, what is our limit approaching? It used to be in terms of x, but now we no longer have x. We're using u. In order to figure that out, we're going to take this equation and we're going to consider what happens when x goes to infinity. Well, when we let x go to infinity, we have u equals 1 over infinity, which then means that we're going to get u equals 0. So that tells us that as x gets larger and larger, u is going to start going to 0. And a way that we can check this then is if we try to solve this limit, we still get 0 over 0. Just like up here, we were getting 0 over 0. That means then that we can do L'Hopital's at this point. Trying to do L'Hopital's on this was not going to be easy. That was the reason why we chose to do it this way. So now when we do L'Hopital's, limit as u goes to 0, derivative of tangent is secant squared. Down at the bottom, the derivative of u is 1. Now when we put in 0, well, secant squared, that's 1 over cosine squared. And then we can put in 0, and we see that we're going to get 1 over 1 squared all over 1. And we find the value is 1. So that means that our horizontal asymptote was going to be located at y equals 1. So the purpose of this was just demonstrating to you that sometimes to solve a limit, you may want to do a substitution that is going to make it easier. And I know that when we start reviewing for the AP exam, there's at least one question in the Barron's book that requires you to do a substitution. So that is everything. Here's the homework assignment. I was wrong with question 41. We already did that, so you can skip that. Otherwise, check Schoology to see what is required and what is optional. Thanks, everybody. Have a good day.